All right. Today we're going to start the first lecture of chapter number 6. And the outline for today's lecture, we'll talk about work-energy theorem, and then we'll solve the problems, carry on discussions, and we will end up with a summary or concluding remarks. As usual, in every lecture, we have learning goals. And the learning goals for today's lecture, the first one, understand the meaning of a work done on a body. The second, calculate the work done by a constant force. The third, define the kinetic energy of a body. And last, learn how work changes the kinetic energy of a body and how to use this principle. As introduction here, we say the simple method we have learned using Newton's laws is inadequate when forces are not constant, meaning the acceleration is not constant. So far, we dealt, when we look at a system, especially when you look at Newton's second law, we said that the summation of the force is equal to ma, or equivalently, the net force is equal to ma. So you have here a constant acceleration. What happens if we do not have a constant acceleration? And in that case, okay, we're going to use energy and conservation of energy. So it's another way of describing motion here. So we're going to use energy and conservation of energy. So today we have the concept of work, energy, and conservation of energy that will allow us to deal with situation when the acceleration is not constant. Now, to start with how we define a work, we say work is energy transfer by a force. So you really have to apply a force to do work. And work on a body does, a force on a body does work if the body undergoes a displacement. So that's now a definition here. If there is a displacement caused by an applied force, then in this case you have what you have, work. So you look at the figure that we have below here. 3 men are pushing a car. Of course, they're applying a force. If the car moves, makes displacement, then in this case, they are doing what? They are doing work. Now, if you look at the cartoon that we have here, you have a block. You apply a force on the block, and you move the block at displacement S. Now, by definition here, the work is defined as equal to the magnitude of the force multiplied by the magnitude of the displacement. And that's what work is. So now we are going to look at the case when work is done by a constant force. So you have here a car, you apply a force, and the car moves horizontally at displacement S. So we're going to use S here as a displacement. So you can take this as the x-axis, you can take this as the y-axis, but you're moving along the x-axis. Now this applied force here makes an angle phi with the positive x-axis. Meaning, if you take component of this force, you will have an x component, which is F cosine phi, and you will have a y component or perpendicular component, which we call it F sine phi. Now, since the car is moving along the x-axis or the horizontal axis here, so this component here, it's what is causing the work. So we defined previously that the work should equal the magnitude of the force multiplied by the magnitude of the displacement. But we have to be careful here. We're only the magnitude of the force that, or the part of the force that's causing the work here is the x component here. And the magnitude of this will equal to F cosine phi. And the magnitude of displacement will be S. So the work here will equal to F S cosine phi, where phi is the angle now between the force and the displacement. Now you're familiar with what we did in chapter number 1 when we talked about multiplication of vectors, and we said if you have A dot B, we said that this is equal to A, magnitude of A, magnitude of B, cosine the angle phi, where the angle is between these two vectors. Of course, we can write this as A, B, without writing the absolute values, cosine phi. So right away here, you can see that we have F, S, cosine phi, and phi is the angle between S and B. And F is a force, which is a vector, and the displacement is a vector. So we can write our work as F dot S. And of course, we call this a scalar product, because what you get out of it, you get basically a scalar quantity. And work here is regarded as a scalar quantity or as energy, which it's not a vector to us. So when you have a constant force, that will be the definition of work. Work will equal to F dot S, which will equal to the magnitude of F, the magnitude of the displacement cosine phi, where phi is the angle between both of them. And of course, if you want to take the magnitude here, you really have to take the magnitude of the force, not just only the that's when we use here as the magnitude of the force. But then we have to multiply it by cosine phi, and cosine phi here will bring in the x component that, or the horizontal component that it's doing the work along the displacement. Is this point clear? Now, the units of this work will have the units of force multiplied by the units of displacement, and the units of force are newtons, and the units of displacement are meters. So you have Newton meter as a unit for the work. We're going to define a unit which we call joule, which we call the SI units, and 1 joule is equal to 1 Newton meter. So the units of work are joule, to honor Joule for his work on heat and things like that. And of course, as a Newton is honored with a unit for the force. So we're going to use units of joule for the work, and 1 joule is equal to Newton meter. And the work here will equal to what? Will equal to F dot S. That's in the case when the force is constant. So in this slide here, a block slides to the right on a frictionless, so there is no friction. If you push on the block as shown in the 3 cases below, the first question is the network done positive, negative, or 0? And what is the effect on the speed in each case? Now, if we borrow our definition from the previous slide, where we say that work is equal to F dot S, which is equal to Fs cosine phi, So in A here, while you're moving in this direction and the force in this direction, so the angle between the displacement and the force phi will be 0, and cosine 0 is equal to 1. So definitely the work here is going to be positive. Now, if you look at the situation here, the displacement is this way, your force is this way. the angle between both of them is 180 degrees, and cosine 180 degrees is equal to -1. So in this case, we say that the work is negative. Now, in this situation, your displacement this way, that the force is this way. So if you look at the angle would be 90 degrees between both of them. So phi here will equal to 90 degrees. And cosine of 90 degrees will equal to 0. So in this case, your work is going to be 0. And that will basically expressing these three different situations. Now in B, they ask what is the effect on the speed in each case. Now you know that you're applying the force in this direction, so your acceleration and your velocity in the same direction, meaning that you're going to speed up, so you're increasing your speed. Now in this case, the force is in the opposite direction, and that's, you have no friction here, so that's the net force. So your velocity and your acceleration are opposite, and that will slow you down. And in this case here, you're applying a force, but there is no friction. If there is a friction, you can take that the friction is related to the normal force. But since there is no friction here, then this force will have no effect, and you will continue with constant speed. But we'll come later to this. Okay, probably after I explain something, I'll come back to this again. So let's take the situation when you are moving a block, or a block is moved from x1 to x2. In some textbook, they may tell you that this is x initial and this is x final, but here we use x1 and x2. And your speed at x1 is v1, and when you get to x2, you have a speed which is equal to v2, and you've done this because you have a net force moving you along the x-axis, and they tell you here the force, or the net force, is what? The net force is constant. So the net force here is doing the work. Now, you are familiar with the equation that we did previously, where we say v2x squared is equal to v1x squared is equal to 2ax, and s here, it's x2 minus x1, okay, which we can use as delta x. So out of this, now I can define my ax will be the v2x squared minus v1x squared over 2s, which is the displacement. Now you know that the net force is going to equal to max, and ax is equal to v2x over 2s. Now I can multiply this by, I can multiply both sides by s. So here I will have fs, and here I will have 1/2 mv2 squared minus 1/2 mv1 squared. So this work here, or the net work, or the work done by the net force, which is the total work here, will equal to the change between 1/2 mv2 squared minus 1/2 mv1 squared. Now we're going to define a quantity here, which we're going to call kinetic energy, and the kinetic energy will equal to 1/2 mv squared. And since the units here are joules, of course the units of the 1/2 mv squared will also be joules, which we'll consider as unit of energy, but we define this as kinetic energy now. So now, if I look at the total work, this should equal to K2 minus K1, where K2 is equal to 1/2 mv2 squared minus 1/2 mv1 squared. In some textbook, you may actually see here final, and you may actually see here initial. Okay. And that basically gives you delta K, and delta K here, the change in the kinetic energy. So the work done by the net force on a particle equals the change in the particle's kinetic energy, and this is known as the work-energy theorem. And total work here, it's equivalent to saying that the work done by the net force. Okay. Well, remember, when we, in Newton's second law, when we say that the summation of the force should equal to ma, and we said this is basically equal to or equivalent to saying the F net is equal to ma. So when you're looking at the work done by the net force, you're basically looking at the total work, okay, because that's defined by the net force. And this equal to the change in the kinetic energy. Now, let me go back to this slide here. When we said what is the effect on the speed. Now, if we say that the work total equal to the change in kinetic energy, which is K2 minus K1, well, in the first case here, you have a positive work. That means K2 is greater than K1, meaning that you have a higher speed because K is equal to 1/2 mv squared. Now, in this case here, the total work is negative, meaning V1, meaning K1 is greater than K2, and in that case, your speed is going to decrease because 1/2 mv1 squared is going to be greater than 1/2 mv2 squared. And in this case here, total work is equal to 0. That means K1 and K2 are the same, which means that you're moving with constant speed. Is this clear? So what we defined so far, we said that work is equal to F dot S, which is equal to Fs cosine phi. And we define kinetic energy as equal to 1/2 mv squared. And then we said that the total work or the net work, which is basically done by the net force, should equal to the change in kinetic energy, which is K2 minus K1. Is this clear? Any question on this? So let's deal with some questions here. And what we have here, it's an exercise. And the exercise here asks, is the work positive, negative, or 0? And they give you here a weight lifter. And they ask the weightlifter exerts an upward force on the barbell. And you can see weights at the end of the barbell here. And they tell you here the barbell is stationary. And they ask the work done by the weightlifter on the barbell in this situation. Now remember what we said. We said that if it causes a displacement, then there is work. But this is stationary. That means if you do a free body diagram, the force applied by the lifter, or you can just take it along the Y, up minus the mg down will equal to 0 because it's not moving. So the force here will equal to mg. But when it comes to work, we said that the work should equal to F dot S, which is equal to Fs cosine phi. And since there is no S, that means in this case the work is 0. But that doesn't mean the weightlifter is not applying any force. No, he's applying a force equal to the weight of the barbell, but it's not moving. Now, in this situation here, the weightlifter lowers the barbell to the floor. So it's moving a displacement S, and they ask you the work done by the weightlifter and the barbell, and the work done by the barbell on the hands of the weight lifter. Now, force applied by the lifter is up in this case, and the displacement is down. So the angle between both of them is 180 degrees, and cosine 180 degrees is -1. So in this case, you're going to have negative work. But now when you look at the work done by the barbell on the hands, so the barbell is pulling down and the displacement is down, so the angle between both of them is 0, and cosine 0 is 1, and that basically will give you positive work. So that's how we look here at the work done, either it's positive, negative, or 0. Let's take an example here where we can work this out. You push your physics book 1.2 meters along a horizontal tabletop with horizontal push of 10 Newton, while the opposing force of friction is 5.9 Newton. And they ask you, in the first case, find the work done by the force of 10 Newton push. So if you look, that's the applied force. The weight will be down, the normal force will be up, and friction, of course, will be opposing your motion. But they ask us the work done by the applied force, and that's why we say work, and then we put F ab, and F ab here means the applied force. So it will be the magnitude of the applied force, the magnitude of the displacement multiplied by cosine the angle between both of them. Now the applied force and the displacement are in the same direction, so the angle between both of them is 0. And the magnitude of the force is 10, the magnitude of displacement is 1.2, and cosine 0 is 1. This will give you 12 joules. So that's the work done by the applied force. The same question, but they ask you here the work done by the force of friction. You know that friction is opposing your motion. And that's why we say here the work subscript Fk, and Fk here friction or kinetic friction force. So it will be the magnitude of the friction force, the magnitude displacement, cosine the angle. Of course, the object is moving this way, friction is that way, so the angle between both of them is 180 degrees. And cosine 180 degrees is equal to -1. And the magnitude of your force of friction is 5.9 Newton, so it's 5.9 times 12 times cosine 180 degrees, and this will give you -7.08 joules. So that's the work done by the force of friction. Here they ask you the work done by the force of gravity. You know that the weight is down this way, your displacement in that way. So if you take the angle between both of them, it will be 90 degrees. So we say the work done, and Fg here, it stands for the force of gravity. It will be the magnitude of the force of gravity, which is equal to mg, times the magnitude of displacement multiplied by cosine the angle between both of them. And in this case, the angle is 90 degrees, and cosine 90 degrees is 0, and that will give you 0 work. We can do the same thing for the normal force. The normal force is up. You're moving that way. So the angle between the normal force and displacement is 90 degrees. and cosine 90 degrees gives you 0. So the work done by the normal force is 0 as well. So when you look at the total work done here, you're going to take the work done by the force of gravity, the work done by the applied force, plus the work done by the force of friction, the work done by the force of gravity, and the work done by the normal force. 12 minus 7.08 plus 0 plus 0, and that will give you 4.92 joules. And this is basically now the total work. Now you can look at the net force, and it will give you the same thing. If you look at the net force and where it's directed and so on, you will get the same value. So usually when we said that the total work should equal to the change in kinetic energy, we're actually looking at the net effect or the net work. Is this clear of how we calculate this? Okay. Now let's look at another example here, and the example that we have here, 5 kilogram package slides 1.5 meters down a ramp that is inclined at 30 degrees. The package slides 1.5 meters under the influence of gravitational and frictional forces, and they ask you here, find the work done by the force of friction. Now, in the diagram here, they give you the magnitude of the force of friction, which is equal to 10 newtons. And they give you the displacement is 1.5 meters in this direction. You have the weight, which is straight down, and you can put the normal force, which is basically normal to the surface here. Now, if you want to look at the work done by the force of friction, it will be the magnitude of the force of friction, the magnitude of the displacement, cosine the angle between both of them. Now, friction and the displacement are opposing each other, so the angle between both of them is 180 degrees, and cosine 180 degrees is minus 1. So 10 times 15 minus times cosine 180 degrees, this will give you minus 15 joules. Now, the work done by the force of gravity. Well, the displacement is this way. So you want to look at the angle between the force of gravity and the displacement. Now, this angle here will be 90 degrees. This is 30. So the angle here will be 60 degrees. And that's why you say that the work done by the force of gravity is the magnitude of the force of gravity, the magnitude displacement, cosine the angle between both of them, which is the force of gravity will equal to mg. M is 5, g is 9.5. So 5 times 9.5 will give you 49 newtons, times 1.5 times cosine 60, and this gives you 36.8 joules. Now you can look at the work done by the normal force. And in this case, you know that the normal force and the displacement, if you look at the angle between both of them, you'll find it's 90 degrees. And cosine 90 degrees will give you 0. So that's the work done by the normal force. These are all the forces that I have here. I have the weight, I have the normal force, and I have friction. So my total work here should equal the work done by the frictional force, the work done by gravity, and the work done by the normal force, minus 15 plus 36.8 plus 0, and that gives me 21.8 joules. So whenever you have a situation, now in this situation that we have here, the frictional force is constant, the weight is constant, the normal force is constant as well. So we can deal with the case when we calculate the work done by a constant force, but we look at the total work at the end. Is this clear? The normal force is not zero. The work done by the normal force is zero. Someone is asking here, how come there is a friction and the force of friction is equal, or the normal and the normal force? I'm not saying the normal force is zero. I'm saying that the work done by the normal force is equal to zero. And that's why you say here ns cosine phi. So if you look at the angle between the normal force and displacement, it is 90, and cosine 90 is 0. So the work done by the normal force is 0, but you still have friction, and there is a normal force which is not equal to 0. Now we'll deal with an example where you're given the force in terms of unit vectors and the displacement also in terms of unit vectors. Steve pushes the car with a force 160 I hat minus 40 J hat in Newton, and the displacement of the car is 14 I hat plus 11 J hat in meters. How much work did Steve do? In this case, you're only doing a dot product, so that's your F, that's your S. You take the dot product, F dot S. So 160 I dotted with 14 I will give you 160 times 14 I hat dot I hat will give you 1. You can do 160 I hat dotted with 11 J hat, but you know when you dot I with J, you will get 0. The same thing here. You can take the minus 40, you dot it with the I, you'll get 0. But minus 40 J hat dotted with 11 J hat will give you minus 40 times 11, and J hat, that J hat is equal to 1. That will give you 1,800 joules. So that's a dot product and how you deal with it. Okay. That's how you calculate work done by a constant force. Is this clear? In this exercise here, we're going to look at the concept of kinetic energy, and they ask us basically to compare. You know that the kinetic energy is defined as 1/2 mv squared. So you're looking at the speed, you're not looking at velocity. So if I look at case 1 here, the kinetic energy here will equal to 1/2 mv squared, because I'm just going to take the speed, which is the magnitude of this velocity. Now, K2 here will equal 1/2 mv squared. Now, the velocity here and the velocity here, they have the same magnitude, but they have different direction. But the speed, which is the magnitude, is going to be the same. So in this situation here, K1 is equaling K2. In the second case here, K1 will equal to 1/2 mv squared, but K2 will equal to 1/2 times 2mv squared, which will give you mv squared. So you can say that K2 equals 2K1 here. Twice. You double the mass, keep the speed the same, you'll double your kinetic energy. In this situation here, your K1 is equal to 1/2 mv squared. K2 here will equal to 1/2 m2v squared. And 2v will give you 4v squared. But you still have the half here, so that will give you 2mv squared. And this tells you that K2 is equal 4 times K1. So, and you double the speed, you quadruple your kinetic energy. And that's the idea here. Is this clear? In this example here, which is going to make use of the Work-Energy Theorem, a 0.6 kilogram object has kinetic energy of 2.5 joules at point A, kinetic energy of 7.5 joules at point B. What is the total work done on the object as it moves from A to B? So at A, that's the kinetic energy. At B, that's the kinetic energy. The work done should equal to K2 minus K1 or K final minus K initial, which should be KB, that means the kinetic energy at point B, minus Ka, which is the kinetic energy at point A, 7.5 joules time minus 2.5 joules, and gives you 5 joules. In this example here, a tractor pulls a sled loaded with wood. Total weight is 14,700 Newton, a distance 20 meters along a level ground. The total work done on the sled is 10 kilojoules, so they give you the total work here. Suppose the sled's initial speed is 2 meters per second. What is the speed of the sled after it moves 20 meters? So if you look, the initial speed here is 2 meters per second. You're going to move 20 meters, and they ask you what will be the speed when you get to this point here after 20 meters. Now, we're given the weight, which is 14,700 newtons. From this one, we can get the mass by dividing the weight by G, and the mass is 1,500 kilograms. Now, they give us the total work, which is equal to 10 kilojoules. And you know, kilo is always 1,000. So it is 10,000 joules. And they ask us what is the final speed, or V2, if the initial speed is 2 meters per second. Now, our definition from the work-energy theorem says total work should equal to K2 minus K1, which is 1/2 mv2 squared minus 1/2 mv1 squared. I can multiply this by 2. That will cancel the half. I can divide this by m, and that will cancel the m from here, and that's why I have twice the total work divided by the mass should equal to V2 squared minus V1 squared. I'm interested in V2, so you can take this to the other side. So V2 squared will equal to V1 squared plus twice the total work divided by the mass. Now they're interested in speed. Speed, you always take the positive square root. So it is square root of V1 squared plus 2W total divided by M. It's 2 squared plus 2 times the total weight, and the total weight here in joules, it's equal to 10,000 divided by 1,500 kilogram, and this gives you 4.2 meters per second. Is this clear? Now we can look at a tractor driving at constant speed. So they gave you a condition now, constant speed, pulls a sled loaded with firewood. There is a friction between the sled and the road. Find the total work done by the sled after it has moved 20 meters. Now, you know the definition. Total work should equal to K2 minus K1. Since it's moving with constant speed, that means V2 equals V1. That means K2 is equal to K1. And the total work is equal to 0. And they tell you right away that you have here a friction. So yes, the tractor is pulling and applying a force, but there is a friction opposing, and that may give you a net force equal to 0, and that means can result in a net or total work that is equal to 0. But in here, we're just looking at the application of the work-energy theorem. The last example that we're going to deal with here, they tell you a block of mass 1 kilogram is released from rest at a height h, which is 1.5 meters above the surface of the table. The incline makes angle theta 30 degrees, as shown in the figure. A 2 Newton force of kinetic friction resists the downward motion. Determine the speed of the block when it reaches the bottom of the incline. So when it gets here, what is V equal to what? And you're starting from rest here. So your V initial here, or V0, is equal to 0. Now, you know that the total work should equal to the change in kinetic energy. And the forces that you have here, you have the weight down, you have the normal force up, and then you have a friction. And they tell you that the friction here is 2 Newton force. So you take the total force, and we dealt with a situation like that before. So your total work here should come from the work done by gravity, the work done by the normal force, and the work done by friction. In the case of gravity, the displacement is this way. So it's the force of gravity, magnitude, times the magnitude displacement, and the angle between both of them, it will be 60 degrees. And we dealt with this before, because this angle is 30 degrees. If you drop this, it will be 90. So that's 60 here. For the normal force, the angle is 90 degrees, and cosine 90 degrees will give you 0. For the force of friction, it's opposing your displacement, so you'll have an angle of 180 degrees. So for the force of gravity, it's mgs cosine 60 degrees plus the force of friction. This is 0 now. For the normal, it's 2, and cosine 180 degrees minus 1. What is the magnitude of S? Well, this angle here is 30 degrees, and this is H, and this is your S here, like what we have there. So we'll have sine 30 degrees will equal to H over S. So H will equal to S will equal to H over sine 30 degrees, which is 1.5 over 0.5. Sine 30 is 1/2, and that will give you 3. And that's why we have the 3 here for the magnitude of S, which is 3. So for the work done by the gravitational force, mass is 1 times 9.8 times 3, and cosine 60 is 1/2 minus 6. That's coming from the work done by the force of friction, 2 times 3 times minus 1, and this will give you 8.7 joules. This total work should equal to the change in kinetic energy, which is K2 minus K1, 1/2 mv2 squared minus 1/2 mv1 squared, but the v1, which is the initial here, it's starting from rest, so it's equal to 0. So you'll have the total work is equal to 1/2 mv2 squared. So you multiply by 2 and you divide by m. That will give you v2 squared, but you need to take the positive root of that to get the speed. So v2 will be the square root, or the positive square root of 2 w total divided by m. And the w total is 8.7. So 2 times 8.7 divided by 1, and this will give you 4.2 meters per second. Is this clear? So the idea here, the total work should equal to the change in kinetic energy. And before that, we learned how to calculate the work done by a constant force. And in all of these situations that we dealt with, your normal force is constant, your force of gravity is constant, and they tell you that the frictional force also is constant. So what we dealt with today is basically work done by a constant force, and we define that as F dot S, where F is a vector, S as a vector, but when you take a dot product, you get a scalar product. That means you're going to get a scalar quantity, which is energy, and the units of that are joules. And we said that this should give you Fs cosine phi, where phi is the angle between the displacement and the force. Then we define kinetic energy, and we said the kinetic energy is equal to 1/2 mv squared. And then we said that the total work should equal to the change in kinetic energy. That means K2 minus K1, or as I told you in some textbook, they may call you Kf minus K initial. But this applies to the total work. You really have to look at the total work and equate that to the change in kinetic energy. I think this is what we want to do for today. Any questions on this? Any questions? Good.